All right, now when you close the mesher, this is something kind of tricky. The mesh needs to be updated here, so you need to right click and update. If you open up Fluent before you've updated the mesh, you can cause all sorts of problems. So that's a big trick there that you're just going to need to remember how to do. So since we've updated the mesh, we can select Setup. It's 3D by default, and under Options, we're going to select Double Precision. All of the other settings are fine. And now Fluent opens up, and in fact, our geometry and our mesh should show up within a few seconds. Okay, steps that you go through. You check your mesh. Looks fine. Under Mesh here, you can do a smooth and swap. And after that, I'm doing it a couple of times. Um, and basically, it will try to make improvements, but usually the best way to make an improvement is to actually have a finer mesh. Unless you get a specific error, it should actually still work. Okay, so that's general. All those are fine. We're going to go to models now. Viscous laminar is what we want. Fluid, we want that to be water, so we have to do the same old trick that we always do. Go to the database, get liquid water, copy, close this, and then highlight liquid water. Cell zone conditions, the interior is going to be fluid, despite the fact that that's called solid. It's just a default name. The next step here is to put in the boundary conditions for the inlet. And we're going to make this a, pressure inlet. But we're going to set the pressure to 0. And the outlet's going to be a pressure outlet, but we're also going to have the pressure set to 0. Any flow in our system is not going to be due to the pressure difference between the inlet and outlet, but rather due to the spinning wall. Okay, so the walls here, they're stationary, no slip boundary condition, but the impeller, it's also type wall, but when we edit it, we're going to make it a moving wall. And we're going to make it rotational with a speed of 10 radians per second. And we need to define the axis about which it is revolving. And so in this case, because of the way we defined it, it should be revolving around an axis that is pointing in the y direction. If you look at the diagram over here, you'll see that that's true. No slip condition applies though. Okay, solution methods, we'll take the defaults. Solution controls, we'll take the defaults. Monitors, for right now, we'll just leave those. Solution initialization, initialize. No errors. Run calculation, check the case, no recommendations, that's good. And number of iterations we'll set to 100. And we'll see what happens. Okay, calculations are proceeding actually really pretty quickly given that this is a 3D flow. And the reason for that is that the number of elements is only 28,000. If you had 100,000 elements, it would run a little bit more slowly, but it would still run. Okay, so 100 iterations have gone by. The continuity residual is still decreasing, so clearly we're far away from convergence. So we'll just do that one more time. And it's improving quite a bit, as you see. In the 3D models, the convergence criteria, or the residuals, don't get as low as they do in the 2D problem. So, when you get down to like 10 to the minus fifth, that might be as good as you can possibly get. Okay, we're going to hit a convergence criterion in a little while here. And the convergence criterion is 1 times 10 to the minus 3. And not quite there, so we'll do another 100 iterations. Okay, and there. We've hit our convergence criterion. It's clearly not converged because if we kept running it, these things would plateau out. But we're just going to go ahead and stick with what we have. All right, we're going to look at contours, and we want to look at inlet and outlet, and we want to look at velocities. We want them to be filled, and we click display. Okay, so they're all blue. The reason for that is that the global range is turned on. If we turn that off now, we're just seeing the full scale of the two objects we've selected, the inlet and the outlet. You can also see the velocity of the wall, which is 0, and the velocity of the impeller, which is quite a bit higher than the flow at the inlet and the outlet, as you would expect. Okay, so that's a good thing. The wall's not moving, but the inlet and outlet are. You can do some additional tricks by adding in surfaces that allow you to actually see what's going on at different planes. Okay, so now we've got this new plane here, and so when we select the contours, we can in fact now add in plane 5. If we rotate this around, we'll see that in fact it is a plane, and that the fluid is moving quite slow at this even small height above the impeller. We can also put in another plane that's perpendicular to that one, and you can do that by doing a point and normal. So we can start off at the origin and then define a normal to that plane. And so this normal we'll see if that worked. Let's see. And there we go. All right, so that particular contour or that particular plane is actually quite helpful in seeing what's happening to the fluid flow over time. Okay, those are the main tricks for 3D pump problem in Fluent, and it should be quite helpful to you in doing project 2. All right, we're going to save the project, and basically we're done.